Okay, there we go.
I guess there's not too much to say, just that the column overflow works now, and that means that you have a choice when you're building your circuit. So I was explaining this to people in Lisbon, and one of the ways that you can think about it is that the circuit just gets basically laid out in 3 columns, and then if we run out of rows, we just continue in the next 3 columns. So it's either 3 or 6 or 9 or whatever, right? Total advice columns that are used. So it's a multiple of 3 right now in most cases. And you'll see that when you run it, it'll say 3 advice columns or 6 advice columns or 9 advice columns or whatever. And of course, there's a prover verifier trade-off. So if you reduce k, the prover will run generally faster, like if it's a wider rectangle. But of course, the proof is larger because there's a commitment associated with each one of those columns. And that means that there's more work for the verifier to do, including maybe too much work, depending on if you're trying to do EVM verification. So you'll see that you could try, for example, the same circuit at different Ks, 16. Right? So the default bit size is 16, so you can't go below 17 unless you reduce the default precision, because the lookup column doesn't overflow. So you can reduce the precision if you want to do a comparison to like a smaller precision, and then try different values of k, and you'll see the prover be faster for lower values of k, and the size of the proof gets bigger.
Is it more expensive to have extra columns, or to have more rotations to access more rows?
So we're not using the rotation is still always 1.
Okay.
Sorry, camera turned off. So the rotation is always 1, or 0, 0 or negative 1. So it's doesn't cost anything rotation wise, but yeah, rows cost more and columns cost more, and the cost function, you can work it out, but it's roughly something like there's a big constant cost. It's not really constant, but it feels constant for when you increase k, and then there's a small cost per column. But those 2 costs compare such that for the prover, it's better to have small k and a large number of columns, and for the verifier, and that's the wide proof idea, and for the verifier, it's better to have fewer columns.
Interesting. So they're both compiled differently?
It's almost the same. It's just that it's like the same circuit, which sort of mentally is just 3 giant columns, but those columns might be laid out in an overflowing way. First we do these, and then we keep going. Yeah.
All right. So I guess. Wait. So rotations got removed from EZKL, right? Because I think it's no longer run argument.
Yeah,
so
the max rotations doesn't do anything anymore. That's right.
I see. So because I'm like working on the functions, and that got removed, so like I was refactoring stuff.
Yep. Because it always right now. I mean, at some point we might start using it again for something, but right now the circuits just use 0 and -1 because it's with such a huge speed up to do that way.
Makes sense. Right. I also have some updates on my end. So I'm actually I implemented 4 functions, so I'm like working through them really gradually. So the main challenge with doing the Python bindings is actually Python itself. So certain types, like for example, like vector f32, like it's not straightforward to convert it to a corresponding Python type, and things like strings and so like the main challenge I have is kind of serializing like output from Rust into something that's Python friendly. So so right now I'm assuming the vectors to be small enough into so that it can be fit into a Python dictionary. So I think there might be memory issues once things gets larger, and if that happens, I would convert things into ND array, so I can use things like NumPy. So I can send a link. So like the initial bindings are in my GitHub branch. So if anyone wants to experiment with stuff, you can actually try.
Yeah, I'd love to. So it's in your. If we go to your GitHub, it's in your branch.
Yeah, it's this one. It's the Python branch.
Cool.
So yeah, I set up some PyTests right now. So for a bunch of them, they work fairly fine. So yeah, the other challenge that I faced was like, how do you actually use like keyword arguments and args? So I ended up using default, like for example, the run args. I left it as a default parameter that you can put within all the various functions. So so I was like deliberating between a keyword args or using the args. So I ended up just like using default parameters, like how SciPy works. But I might refactor that into an object if that's something that's going to be reused all the time. So you might want to declare like a runargs object and include that into every single argument of like the function that you're going to use. Yeah. So generally, I would try to get things done as soon as possible. It's just like yeah, it's actually slightly trickier than I thought it would have been. So I thought this would happen fast, but yeah, but converting between Python and Rust in an idiomatic fashion for both languages is actually quite tricky. So
Yeah.
and any other error that that I faced was like it's like serializing the errors into Python. So that was actually another challenge. So like on Rust, you could simply use the question mark thing and like tada, it would handle the errors. But apparently, like some of the errors are not handled in Python, so you have to kind of write like wrappers for that. So for now, I'm just like using match and just matching it to the corresponding Python errors and just making things more explicit in this regards. Yeah, fairly tricky. So like PyO3 is apparently not as well as in there's not much like resources online for that. So I'm just like combing through the whole documentation of PyO3 and finding like what actually works. So yeah, gradually like working through them. So so right now, if you actually compile like the EZKL branch, and that there should be this you can import EZKL _lib and you should be able to call like the various functions like forward, mock, table, and later on the what is it, generate proof. So I'm trying to like get the so the function calls are going to be similar to how you would call EZKL. So it would be like like EZKL _lib dot forward and using is it kebab case or sorry, it's camel case, I think, or is it camel case? Wait, what's the underscore case thing called? I forgot what it's called. So it's like
Snake, I think. Snake, yeah.
Snake case, yeah. It'll be all in snake case to make it idiomatic to Python. Yeah.
Yeah, that's cool. But yeah, it's so hard to make something idiomatic. It's not just a matter of it's just a matter of exposing the function.
And because I also like one thing yeah, I'm also still kind of struggling with this aspect because like on EZKL, like you're outputting into like standard in and standard out, so you'll be outputting to files. But in Python, that might be a little bit annoying because you don't want to be importing JS on files. So yeah, so serializing this into the Python dictionary so you can use it for other functions is also quite tricky. So yeah, but that I'm more or less like working through all the various functions. So I think it's like 4 or 5, and yeah, I'll be pushing code. And once I get more or less like the functions up, I think I can start merging it into main and like hope to get some code reviews and then like see how it goes. So I guess in this respect, maybe like Lance or Amit, like would you rather import EZKL lib or just use like PyEZKL, because there's another separate PyEZKL repository? Which like would it be better to just use PyEZKL? Because I think like right now it's like the library will be compiled within the EZKL lib itself.
Yeah, that would be great. I think I tried to use PyEZKL one time, and yeah, that would be great if you could bind it into one. Yeah.
Cool. So I guess
I've used it for generating the Onyx files and everything, but from what I see in your test files, it's like you could just call the functions from the commands, from the EZKL commands right in the Python script. and just
Yeah.
provide the arguments. So this is amazing.
Yeah, it's yeah. I'll try to get them done. Like I'm still working through them and figuring like what to actually even do at all because it's actually much harder than I thought. So like yeah
Yeah, I actually I wanted to ask in terms of providing the directory for the Onyx file. What would that look like with the like OS path directory name? Would it just be anywhere that you have the file stored, or would those Onyx files have to be inside of the Python project?
Oh, right. So for that, how I'm intending for that to be used is that there are a few approaches, right? So one of them is to provide the ONX file within Python itself. So it could be a Python dictionary. The other option, which I think might make more sense, is to load the ONX file. So you would provide the path. So I ended up using that approach instead. So because I'm not sure how large
to load it like into Python, like into a buffer, you mean?
yeah, you have to load it into a buffer. So like the buffers are used within Rust itself. So what's happening is that you're going to provide a string within Python, and what happens within like the Rust backend, it loads a path buffer and puts that into the EZKL functions in Rust itself.
Yeah, imagine that people will also want to use it without ever putting it in a file, right? Like there's the Python Onyx package, where you can use it to directly create Onyx files, and of course there's the torch export stuff. But I'm hoping that people will be able to just kind of freeze the graph and then directly send that object. I guess it's fine if it's serialized, but I don't know. Like maybe the Onyx only in some cases the Onyx file might only exist as a buffer because it's just being used to communicate, you know.
Yeah, so this is also another challenge with Rust and Python, right? So Python things are not like Rust things are explicitly typed. So yeah, so it's in Python, like you would want things like maybe this is an like the ONX file from the ONX library, or this could be a path, so it could accept both. But I guess in Rust, like that gets slightly tricky because now you have two different cases to handle. Or I guess another possibility is doing some kind of function overloading, but I'm not sure whether that's possible with like the PIO tree stuff, or you get to like a function signature collision. Yeah, but that's why like I think I can also look into if, let's say, you would like people would rather not use the ONX file and use it directly.
Man. That's really cool. Can you bring up or mention the library that you were referring to again? You said PyO3?
ONX? The ONX one, are you referring to that?
Yeah.
Let me find that.
Well, do you mean the Python one or the Rust one?
The Python one.
Right.
Yeah, it's just called Onyx. So like if you can import once you have it, ONNX,
yeah.
and that's the one that lets you manipulate without PyTorch directly kind of write Onyx files, which is probably something that.
Okay, got it. Is the pip install Onyx one, right? Okay.
Yeah, exactly. So yeah, I guess it might be cool to just have import that directly within Python. So you can so instead of like writing it to a file buffer, you can actually just use it, because I think like there's already like inbuilt ONX stuff within Python. Okay, this is tricky. So it feels like to me.
Also this. There's also this simplifier that we've been playing with. There's this Onyx simplifier, which you can also use the library, I think, but which is nice for manipulating, deleting nodes, or just as a general Onyx. You can use the Onyx to delete nodes, because, like, for example, we often want to delete the final output node, which is like a class or something, and just keep the vector. Or we want to run this simplifier, and that lets just link, which lets you, merge affine layers and get rid of some of the garbage. Because sometimes when you export Onyx, it puts in all this garbage, which doesn't really do anything. Just like, you know, it's no op, but it's expressed in some complicated way. Scatter, gather, and all this stuff. Yeah.
Been using that a lot for the larger models that just have a lot of extra layers when the Onyx file is created.
And not to suggest you need to worry about it now, but just so it's on your radar that probably people will want to manipulate their Onyx files. You know.
Yeah.
Oh, that would be cool. If they could use the Onyx.
You know, manipulate it, and you try EZKL, you see there's a problem, you manipulate it some more, that kind of thing, make it more iterative.
Right. That actually makes sense. So I guess like one. So I guess that's also another challenge. So like passing an ONX type within Rust. So because that is not like a Python object. So I guess I can gradually look into that. So I think I was just like the path buffer things to like have a correct functioning first, and once like I figure out about how can I actually import like the Python objects within Rust, that'd be really cool. So you can like use like the ONX library from Python within like the Rust object, and yeah, it becomes really handy to use. So, but right now because it's just like a path, and I think also EZKL uses like the path to manipulate things, the ONX file within the execute function. So essentially what I'm doing right now is I'm like looking through all the execute functions and porting it over to a Python friendly version. So that's what's happening. So yeah, we'll have to learn more about like how the Python imports actually work, because so like the challenge right now I think is that within Python like you have like a GIL, the global interrupt block. So how things run within Python and Rust like works quite differently. So it's not like a easy kind of port to do, but that's something I can.
I don't think we want. So just to be clear, because I think I might have suggested, it sounds like I was suggesting this. I don't think we want any Python to run from the Rust side. Like EZKL should not depend on Python. You know. Or use Python libraries, because that will make it too. That's sort of cryptographically a little bit scary.
Yeah. Oh wait, I have an idea. I have an idea right now. So okay, so on the EZKL lead, like it could use like the path buffer again. So but what happens is that on the PyEZKL, like it would still import like the ONX file. So essentially PyEZKL could have like wrappers for the backend function.
Yeah. That's the idea.
Yeah, I think that makes more sense. But versus putting it in
install, import it, and then be able to run the function.
Yep, that's mostly it on my side.
Cool. Thank you, Jason. This actually has me thinking. Would it be possible to build out the Halo 2 library with Python bindings?
It's possible. I guess like, the only catch is that like certain cryptographic operations in Python are going to be quite crazy to do.
Yeah.
As it is possible, it's like it's still like Turing complete, but the problem is like the way Python operates, because there's a version like the Python virtual machine, so it gets really slow when you run cryptographic operations.
Yeah, and I feel like the dynamic typing would be an issue too, because you need to define every cells type.
Yeah, you can make Python strongly typed. I think with like the Python 3.7 or 8, you can actually define the types, but it's not strongly enforced. So like things can still run. It's just that you can do like static checking to check whether the types match up, but it will not fundamentally stop the code from running.
Wait, so how does that work? Do you just change something in the config file?
No. So within Python, like you can declare things like a colon dictionary or dict. So you could define like types. So you could declare a class and and essentially define like the variable. So on a Python function, it'd be like function like def a and then your function. Right now you can do like def a colon integer and then your function. Yeah, it's just like a new thing.
Integer as a parameter, right?
So sorry, I didn't catch.
Integer as a parameter, right?
Yep. So it's like all the list of Python objects. So it can point to a Python object. So you can also define your own custom objects for those use cases. Let me find the
Okay,
link.
so the compiler isn't expecting any strongly typed values. It's just that you have the option to strongly type them.
Yeah. So
Yeah,
I think
okay,
it's only introduced in like Python 3.7 onwards. I can find the link.
Yeah, I feel like it would be cool if there was something that you could put in the configuration file that makes it statically typed. Well, I can talk about the Euclidean distance operation that we've been talking about for the Face ID feature. So we're training a small model to just get the basis done of what would it look like to have an on-chain verifier for Face ID. And what we want people to be able to do is kind of store their own we're calling it like a target output, but it's kind of like a vector that represents this person's face in the machine learning model. And what you could do is pass in your target and then pass in a pre-image of your face, like a picture that you take of your face. And then the machine learning model will run on the pre-image and generate a new output tensor. And then you find the Euclidean distance between what the face is and what it should be. And if that Euclidean distance is small enough, then you give the person authentication access to, maybe send a transaction with account abstraction, or, sign a transaction, but basically making it so that you can use AI for authentication purposes with EZKL. And what I've been working on is a Euclidean distance op that we just put in EZKL, where you just can pass in some type of structured tensor. Maybe it's like a vector of 10 values, and then you can say, hey, this is what the format of my target is going to be, and you can have users authenticate by calling this function in EZKL that then calls maybe like the verifier function or the verifier in WASM, or any type of verifier. So it's cool because we've been talking about the Face ID project for a while, and even though the model will have to be relatively small, I feel like in the future it could be a real thing for account abstraction.
Cool, sounds cool. Oh, by the way, have you looked into things like hard cascades? So they are kind of like more traditional computer vision approaches, which are not necessarily like deep learning based. So
Yeah, can you say it
I'm
one
not
time?
sure. A hard cascade. So open.
No,
So I use this for I guess I think it was an embedded electronic solution, because there was also like similar computational a limit. So instead of using like just deep learning approaches, so I ended up using things like hard cascades and edge detection algorithms, which have like lower computational bounds. So I guess it might be interesting to also maybe maybe use those kind of transformations to maybe reduce the kind of computational size required, and then fit that into a deep learning like ML model if that is required. So it's just like a workaround if, let's say, like performance is not as ideal. So those are things that could be into. Let me find the link for you again.
For sure, I would appreciate that, because I feel like right now we're not 100% looking for performance. It's more so of what does it look like for this to actually work. would it make sense? Like where would it make sense to store people's output tensors? I feel like that's one of the biggest problems that we are facing. Thank you for this, Jason.
Yeah, so it's actually a much simpler thing. So it just looks for it's a kind of form of template matching. So that's essentially what the hard cascade classifier does. So you can specify some kind of classification, and then afterwards it will it will classify things according to the template. Yeah, but it's written in like OpenCV, so I'm not sure. But I don't think this can be processed easily. But it's an approach to also consider. So I guess that could be an input, like for EZKL, that could be an input feature, and instead of using like a RGB, which is like if you have alpha, it'd be a 4 by X by Y kind of tensor, which is quite a huge data space. So you can use this as a dimensional reduction technique, and then pass it into something like EZKL, which could enhance like performance. So I guess like this is where the Python things come in handy. So it becomes like quick to run this like tests like what kind of features to actually do. So I do think like some amount of feature engineering might actually improve like the performance by quite a fair bit, maybe about 5 to 10%.
I mean, this looks worth it though. You mentioned that the size though, the tensor size was 4 byte height by width. What
yeah,
what are the channels there, or the the 4 represent?
Yeah, RGB, if like, so it could be 3 if you omit alpha.
Oh, okay. And then I actually see it in there. They have a Python implementation, but it uses OpenCV library. So
yeah.
I wonder if there's a way to kind of make this into, or do something similar but in PyTorch.
So yeah, right. So how you would do this is that so OpenCV Python, I think, works with like NumPy. So what you can do is like do a transformation of like the inputs into a output that can fit into PyTorch, because it's ultimately an ND array that you can actually use within Python. So you can use things like NumPy and then fit into PyTorch and load the data as accordingly to what PyTorch actually wants.
Mm-hmm.
Yeah, so that's how you could potentially do it. Yeah, if you need any help, I can also help you with this kind of stuff. So I used to do I used to do like some OpenCV stuff mainly for actually radar imaging. So I was like doing radar stuff like in particular like this thing called synthetic aperture radar. So that's how I got in like acquainted with like embedded electronics and OpenCV stuff.
Mm-hmm. It was called electronic.
So sorry, embedded electronics. So essentially I was trying to do ML on a microprocessor.
Okay, on a microprocessor. That's super dope. And OpenCV was small enough to do that.
You would have to extract like the kind of functions that you actually want. So you also want to make it really lightweight, and if you can find like certain hex, you should use it. Yes, so like that was actually meant for a component like within like some kind of like military device. So there's this thing called synthetic aperture radars, which is also an interesting technology by itself. So like normally on radars you would expect it to be a dot on the screen, right? So using like synthetic apertures, you can actually convert like a radar signal into an image. So it allows you to see different kind of things using like radio waves.
An image of what though? Is it the
radar
image of the radar result?
Yeah, the radar result. So you can actually like convolve that signal and turn it into an image.
Got it.
I can send you a link again.
Yeah. So it would basically simulate a radar, but it would send images of the results.
So it's kind of like so for example, if you have like a normal radar, right? So you would send a ping and you receive like a output from that signal. So that was
Got it.
So
I
so
get
that
it
would
now.
constitute one sample. So the problem is that for for like electromagnetic waves, like the aperture size would correspond to like the kind of image that you actually get. So the problem is that radio waves are really long. So you need a massive aperture to turn that into an image. So the idea for synthetic aperture radars is that instead of like having a physical aperture, you can create a synthetic one by collecting various samples at different points of the sampling using radio waves, and you would essentially apply a convolution operation across like the samples, and you can form an image out of the radar signals.
That is so cool. Wait, so how does the neural net know what a certain surface should look like though? Is it like, is that from the result of the radar? Maybe it knows that there's vegetation in one space. It knows that there's, sand in one space.
Yeah, sort of. So like yeah, I guess like the data set for this that's like a declassified one called sensor, but yeah, but this are kind of like classified information that I think like defense research companies would have that information, but it's not like information that you would find readily online.
Yeah.
Because like this same tech could be used for weapons and stuff.
Yeah. Man,
So like the reason why
they made the image of the surface of Venus with this.
yeah, so like the cool part about radio waves is that it can penetrate the water vapor, so you can actually see through clouds. So it's handy for surveillance equipment. Hence, like synthetic aperture radars are of interest.
This is super cool. I mean, in terms of EZKL, I feel like if you were to have maybe some like decentralized global surveillance system that everybody can trust that the images are valid, because everybody knows the model, or everybody trusts the model, I should say. You don't really know it.
For disarmament, right? Something like that. That's cool.
Yeah.
Kind of like the climate thing we were talking about last time, but but for other common goods.
Yeah, this is super cool. It's something. These recordings are fire. It's something new every single call. Thank you for sharing, Jason.
Yeah, it's fun. Yeah, but I guess like most of the stuff that I did, like in my, it was actually for my internship, but I think it's probably like classified stuff, so I shouldn't be sharing too much of this.
We'll keep it on the low. We'll keep it hush. Cool. Yeah, with that, that was everything that we had on the agenda though. Anybody else want to bring up anything like projects?
There's Lakshman Gandhi.
You say that one more time?
Lakshman Gandhi. There's another fifth person in the chat.
Yeah.
Yeah, hi guys. I work at a VC fund and I'm mostly on the research side. Not building anything, just
Okay.
interesting discussions. Yeah.
Awesome.
Cool.
What are you researching?
Yeah, so I found EZKL through the zkml chat, and on zkml I looked into Modulus Labs, also talking to Jensen in a while. Giza is also quite interesting, but yeah, in general exploring where all these could fit in on the commercial side. And also looked into Percept, actually, Jason. I think you are also like working on it with a few others. But yeah.
Yeah, there's a whole, we don't talk about it much on this, but there's a whole nother angle in DeFi for this stuff, which increasingly looks like it's going to require kind of a more custom stack or a layer between just a lot more work. Basically, to bake in the domain knowledge, and there's different types of functions, and a lot of things are kind of linear and time series instead of deep learning and stuff like that. I think we can support it, but yeah, it's a little bit of work to do.
Yeah.
I've been working on the theoretical side of that actually the last couple of days during my downtime. So
Okay. Okay.
hopefully we'll have some updates there too on how to make this EZKL smarter on
Hmm.
like time series.
Very cool.
I guess on that front, like it might be interesting to just like convolve, like use like the convolutional neural networks and then convert a time series to an image. So I saw like papers like I guess like a few years ago that was doing it and it got like decent performance compared to RNN.
Yeah, just turn everything into a sequence and put it in a transformer, right? That's the modern approach to.
Yeah, like
That's how we do statistics now. That's all, right?
well, right, I guess like
Just stick it in a transformer and ask for the answer.
yeah, I guess also my and I'm yeah, I'm kind of like looking into like the ZK SNARKS more, and I'm and because I think like it uses like discrete logs, like and like the trusted setup and stuff. I'm like trying to see whether there's like a possible like quantum computing attack vector on that. So like that's actually one thing that I'm not sure of because I was like looking for any kind of like literature and then it seems like there's not much like I can't find any like if you guys have any like research to point to that, I think that
Yeah, I was talking about this actually today in my meetings in Dubai, spontaneous meetings in Dubai that Sarah helped me out with. But so I'm not really an expert, but I'm like knowledgeable about enough. I've written a few papers on quantum information and stuff, and with physicists though. Like I wasn't the physicist; I was like the mathematician. And I mean, my take on it is basically quantum. Yeah, I mean, in theory, quantum computing certainly can solve discrete log. But as far as I know, solving discrete log requires entanglement, which has a bunch of different measures, but it's essentially tensor rank that grows exponentially with the size of the bit, the number of bits, right? So nobody can make a quantum. Yeah, so the number of bits in the in the discrete log problem, that like the hardness security factor, and so nobody really knows how to make a quantum. People can make practical quantum computers in the sense that they exhibit non-trivial entanglement and they are hard for a classical computer to simulate. But as far as I know, no one, and my knowledge is very out of date, so this takes a big grain of salt. But no one's been able to make a quantum computer that exhibits the kind of scaling in sustained entanglement that you would need to do discrete log, right? In fact, I think it's a really interesting physics question to ask about whether there might be actual physical limits on that, what we can create. Or like there might be there might be a sense in which this is a lot of people have thought about this, and it seems unlikely, but like real physicists will say it's unlikely. But this question of like, is quantum kind of a linear approximation to something else that will break down if we try to create these exponentially large entanglements and do computation with them. But anyway, we haven't really been able to create them in the lab, and so until that happens, we probably won't see discrete log getting broken. And it's completely separate from like, yes, you can make a quantum computer that has non-trivial entanglement, but the structure of the entanglement is such that it's not useful for factoring or for discrete log problems.
right. I guess on the front, like I got like so I did like some research in quantum information too. So I think like this came back to my radar because I saw that IBM like produced like a quantum computer with like 400 qubits like not too long ago. So if you have like the most like the theoretically efficient like ever correcting codes like this, which is like five physical qubit to one logical qubit, at least you have 80 qubit logical qubits right now. It's still not useful for like any kind of like cryptography cracking application. But I feel like there could be a point where like this attack actually becomes like feasible. And I think like one precipitating design of quantum circuits might be with like topological quantum qubits, like topological qubits. So so I'm not sure what's the status on that. So I think like the one at IBM like relies on like the superconducting, like the squids. So like that's kind of like the approach I think everyone is still using because it's like feasible to produce them in size. Yeah, but Microsoft did announce that they actually created like a topological qubit like not too long ago. But I haven't actually seen any kind of like significant publications around that. So I'm like taking it with a grain of salt. But yeah, but my guess is that in the next like maybe 5 years, like like an attack starts to become more and more feasible given like the rate, like the number of qubits are being produced. So like I guess for
so what I'm saying though is it's like a matrix. I can say I can do a 400 by 400 matrix, but oh, by the way, it's an identity matrix. You know what I mean?
Yeah.
It's very different from I can produce a 400 by 400 matrix and it's any matrix. You know?
Mm-hmm.
So I guess like that then like that deals with the sparsity of the matrix. So I think that was actually like the problem with like the like the matrix operation that I think like showed that you can actually like invert a matrix in log time. So I think that was the one by I can't remember who, but that was a while back. So it turns out that the matrix had to be sparse. But I think like for the discrete log and the what's that? The discrete log and essentially like the hidden subgroup class of problems with the factoring algorithm. It can be solved with like the quantum Fourier transforms. So like I think like the error like the number of qubits like the bound might actually be lower. So probably maybe like within 10,000 qubits. So not anytime soon, but it might be a feasible attack. So
10,000 of these weakly entangled qubits will be enough to break
yeah, that's my guess if you apply like error correction. So that would give you around like 2,000 like divided by 5 with a efficient compiler that gives you around 2,000 logical qubits, which would be feasible for to maybe like crack something like a 20448 RSA bit number. So you can load that into like the quantum circuit. So and suppose if like quantum memory gets created, maybe the bound actually gets reduced. So if you can like split it into like different sections and solve it like separately. But I guess for like large numbers, like they have to be done all at once. So you do need at least like I guess like 2,000 qubits, logical qubits for that case. So yeah. So but I haven't actually found like a mechanism by which like the discrete log for like the trusted setup could be broken. So that was the part where I'm like trying to see whether there's any potential effects on that.
Yeah, because that's a stronger assumption, right? Kind of.
Yeah, exactly.
You have more information. Yeah. I think that's actually interesting. Like, I agree, that's interesting. There's like, there could be something dangerous in all the extra assumptions that we're making here.
Yeah, so I guess like the simpler way out is essentially like change like that trusted setup for like a ZK snug. So but I guess like if you convert the different form, becomes sort of more like a stuck. So but essentially like, I think that's like the point of failure. Like so if you can kind of break that portion, then like the zero knowledge property of a snug might not actually hold. So that's actually one like it's a hypothetical that I'm actually concerned about. So suppose like you think like the snug is secure, but given sometime in the future it stops becoming like a zero knowledge system.
So in that case, do you think if that assumption holds, do you think that SNARKS would be adopted like a lot more than SNARKS?
Not yet, right? So the problem is that I haven't found like a mechanism by which like a ZK snug could be broken. So this is like just a hypothetical right now. So it's not so it's kind of like a non-threat until someone figures out how to like use like the Shaw's algorithm to break like the discrete log in the snug, and then and then kind of extract some kind of property out of the SNARK by virtue of breaking that discrete log. So essentially, I'm like trying to find like documentation or any kind of papers about this, which I'm not aware of any kind of like research on this at the moment. So it feels like to me it might be a it's a non-issue right now, but it could be an issue maybe in about 5 to 10 years ahead.
Believe it.
What is the relationship between bits of security and qubits? I'm not familiar. Like how many qubits do you need to break like in bits of security?
Right. So the reason why this the specific algorithm we are looking at is the factoring algo, like the Shaw's like the algorithm created by Peter Shaw. So so like how this works is that you can actually apply a discrete log, sorry, not a quantum Fourier transform onto a hidden subgroup problem, because there's some kind of periodicity associated with that. So on a normal computer, you can't actually do this, but on a quantum computer, because of like your superpositions and entanglement, you can extract the periods in an efficient way, like in logarithmic time, versus an extremely long time on a classical computer, which makes this kind of hidden subgroup problems like vulnerable. So things like discrete logarithms, prime factorization, like so those fall into the hidden subgroup problems. But the thing right now is that people still do not know like P equals NP or the quantum analog BQP, which is it stands for bounded quantum polynomial time. So BQP is like the equivalent of P, but for quantum computers. So nobody also knows that BQP equals NP. So like all these various complexity relationships are still kind of unknown. So hence like it's not called like quantum prevention, but it's more quantum resistant, because people haven't thought of a good solution to solve those certain problems with a quantum computer. So like right now, I think like the best candidate at creating a quantum resistant system is like things using lattices versus like prime factorization, like for your RSA and your elliptic curve stuff.
Mm. Interesting. Yeah, I've definitely heard lattices being talked about a lot. That's cool. Do you think there's going to be some implementation of like hash functions with lattices?
I think that already. I think like either NIST or some other like research groups are creating like a post quantum cryptography. So it has been an ongoing research, but I think the actual challenge is then like porting over every single crypto system that is vulnerable to quantum attacks to this form. So like what's happening right now is that various like military institutions around the world are essentially collecting encrypted documents for the purpose of cracking in the future for quantum computing.
Wow.
Yeah. So like which is why like there's a race to build like a quantum computer because like this does give you quite an edge. And it's not quite scary, right? Because like human society is kind of advanced, but we haven't really like progressed beyond like the feudalistic tribalistic mentalities that we had from over 1,000 years ago, and now we have nukes. So yeah, it's not a good mix.
Yeah, not at all. And especially when you said just about the encrypted documents, I can only imagine how hard some people must be working just to encrypt. I mean, just to break encryption algorithms to get some valuable information.
Yeah, definitely. Yeah, I'm not sure what's going on right now, but I'm pretty sure there's probably like a bunch of teams just like trying to crack this and secure an itch for whatever purposes that they have.
Yeah.
But right, if you want to try out like quantum computers for real, there's actually this thing called IBM Q Experience. So you can actually have access to a 100 qubit system. Let me find this. So it's actually available for free. I guess with the 100 qubit systems, you do need to apply for, like get a research license or something. So
Interesting.
it might be interesting to actually try it out. So I used to work on like the 20 qubit system. So it was kind of like not very useful for any practical case, but was interesting for quantum communication systems where you don't need so many bits to communicate.
Yeah. Interesting. Okay, so I'm actually gonna make a login here. Is the programming language something that is common, or is it like a specific programming language for this?
Oh right, it's just Python. So the only catch is that it's not like you have to code in like the quantum circuits. So you do need to understand like how like quantum computing works. Like mainly you can see as a superset of reversible computing. So because
that's a super fun rabbit hole, that question of like languages for quantum computing. If you ever want to spend a decade,
Spend a decade.
I recommend it.
yeah, so I did work in the research team. So like they came out like the PI I was working with like founded a company called Horizon Computing.
Okay.
So they're doing like compilers for quantum computers. But essentially, like they're doing like I call it entrepreneurships. Oh man, if this record I shouldn't say this. But essentially, like they're just earning money from grants and yeah.
Field farming. Yeah.
Grant farming.
You know, Lance, that thing I sent you last time we talked, the Selinger stuff.
Yeah.
Those people work on. In fact, that same guy was an author of a language for quantum computing.
What?
Yeah.
New
So
language.
it's a very deep rabbit hole. Yeah.
Interesting. So, what are they similar to?
Because it has this linear typing, which is kind of like Rust in the sense that instead of explicit clone, like you can't clone. There's a no cloning theorem, so you cannot copy. You know, there's no gate that copies a vector. It copies this quantum state, for example.
Yeah.
Stuff like that. Yeah.
Yeah.
So there's a different. Yeah.
So I was also proposing like one approach using like lambda calculus. So yeah, but it's all a rabbit hole. And it's kind of like in a way it's kind of like a time sink because like the machines do not even exist. So it's like it's really like I guess like yeah, it's not very fruitful. So hence I was like doing like more crypto stuff later.
That is cool though. I'm gonna Jason, which author was it?
And Jason, maybe you ran into this. You know, like the graphical languages stuff. The paper was Selinger, but then there's lots of. So he in one of these programs on quantum computing, I think he was the author of one of the languages. I don't remember the name of it. Or his research group. He met him as PI, I think, and then there was a related stuff that some folks at Oxford do a lot of stuff in this area.
Yo, that is super dope.
It's all like category theory for quantum computing kind of stuff. Yeah.
Okay.
Yeah, it's a lot of relationships to what we're doing. Actually, to me, it's quite tightly related.
Really, yeah. I mean, I feel like everything in this space is related in some way, especially, I mean, like math and computer science, you can find a way from one end of the spectrum to the other just from connecting different disciplines. But yeah, I found Selinger's archive page. Interesting stuff. But yeah, okay, cool. EZKL call on quantum computing and some radar machine learning. Look, these calls are great. I'm gonna stop the recording right here.